Hi folks, today we want to start talking about power series solutions to differential equations. And sort of the typical poster child for something like this is an equation called Airy's equation. Airy was an astronomer, and I think originally this equation came up in the diffraction of light. And Airy's equation is y double prime minus xy equals 0. And you can have a couple initial conditions, whatever they happen to be. We'll see what these pop out to be here in a bit. So if you look at this equation, what do we know about it? We know that it's linear. We know it's homogeneous. It's not constant coefficient. We can think about what the solutions might look like if, for example, x is less than 0. Then we get y double prime plus a positive number times y is 0. And that's going to give us oscillations. If x is bigger than 0, then we have y double prime plus a negative number is 0, and that's going to give us exponential solutions. Exponential. So we can sort of glean that from the equation itself. But as far as how we would solve it, it doesn't quite fit Cauchy-Euler, right? To be Cauchy-Euler, we would need to have like an a2 x squared plus an a naught y is 0. And that's not what we have. We've got an x sitting there. And we would need a constant sitting there. So, oops, a naught, a2 x squared y double prime, I should say, plus. Right, so we get that. And so what we're going to do is make the following ansatz. Is that y is, whatever the solution is, it's a nice enough solution that we can express it in terms of a power series. Right, so that's how we're going to solve it. So let's remember a couple of things about power series. If I write y that way, we're going to center it at 0. So this is really a Maclaurin series. And there's some, we're going to assume that this converges for some positive value r. All right, so for some positive radius r could be infinity. Looking at this differential equation, we don't have any singular points we have to worry about, right? Singular points, remember, are places where the leading derivative, the coefficient of the leading derivative is 0, which we don't have any of those. So remember, we can think of this with the convention that x to the 0 is 1 everywhere, including 0, which is a bit of an assumption there. But really what we're doing is it looks like this. That's what we mean by the infinite series. So more or less, we're defining the n equals 0 term to be just c naught, even when x is 0. So when I take derivatives of this, what happens? Well, that's gonna fall away, and I'm going to have a c1 times derivative of x plus 2c2 x to the first plus c3x squared. And so when you're within the interval of convergence, we have absolute convergence. And so we can take derivatives like this term by term. But what happens then, right, is if we take derivative term by term, cn's are a constant. We distribute the derivative through the summation. We get nx to the n minus 1. And the first term has dropped off. So the counter now starts at 1 instead of 0. And then the same thing happens for the second derivative. We take the derivative term by term. And so we would have a cn n n minus 1 x to the n minus 2. Once again, just taking the derivative of this, assuming we can pass things through the summation and the constants. This is going to start then at n equals 2 to infinity. The first two terms have dropped out. So what we do is we take these and we stuff them into our differential equation. And the unknown things here are the CNs. And so that's the goal, is to figure out what the CNs are. So if we put this into Airy's equation, we get the sum n equals 2 to infinity, Cn n minus 1 x to the n minus 2 minus x times the sum n equals 0 to infinity, Cn x to the n equals 0. So I'm just plugging in my assumption there. And once again, assuming we're within the radius of convergence, then I can multiply the x through term by term. And I get Cn x to the n plus 1 equals 0. And now I have to think about what sorts of terms are going to get kicked out here. So if I look at this sum, when n equals 2, I'm going to start with an x to the 0 power, which once again we assume by convention that that's 1. Here when n equals 0, I'm going to start with x to the first power. So after I kick off the x to the 0 term, everything in this series is going to have the same powers of x as this series. And so we're going to want to combine them together. So what I'm going to do is I'm going to kick out the n equals 2 term here. And what would that be? Well, that gives me a C2 times 2 times 2 minus 1. And then I'm going to have a series that starts at 3. Minus this series equals 0. And so now both of these series are going to start with x to the first power and continue on forever, which means I want to combine these series, right? In order to combine them, I need to re-index them. All right, so I look at what I have here. I've got this constant plus all these things equals 0. This is the only constant on this side. The only constant on this side is 0. So I get automatically a couple of things. I get 2C2 has to be 0, which means C2 is 0. So that's something I'm going to tuck away for use later. And the second thing I need to do is I need to re-index the remaining series to combine like terms. And so this is what I do. For me, this is the easiest thing. The way we're going to know if they're like terms or not is if they have the same exponent. So I'm just going to relabel k to be the exponent on each of these. So let's look at this first sum. I've got the sum n equal 3 to infinity, Cn, n times n minus 1 x to the n minus 2. I'm going to let k be n minus 2, which means n is k plus 2. And so what does my new series look like in terms of k? Maybe I'll keep this all in red. Oops. So let's see, n goes from 3 to infinity. K is n minus 2, so k is going to start at 1 and then go to infinity. C sub n is going to be c sub k plus 2. N is k plus 2. n minus 1 is going to be k plus 1 x to the k. So all I did is everywhere I see a n, I replace it with k plus 2. N starts at 3 means k starts at 1. All right, so this is just like changing the limits on an interval, on a definite interval. Now let's take the other sum, n equals 0 to infinity, c sub n x to the n plus 1. And once again, I'm going to let k be the power on x, because those are the things that are the same now. This means n equals k minus 1. So what do I get here? I get the sum. Well, when n equals 0, k equals 1. N goes to infinity, k goes to infinity. C sub n, which is c sub k minus 1, x to the n plus 1, which is x to the k. So now, when I look at the reindexing on the series, I've got the same powers of x, and I've got the same, or I've got the common start point on the index. So I still have C2 equals 0. I'm going to keep up there. But now my equation looks like this. I've got the sum, k goes from 1 to infinity. And I'm just going to write this down. ck plus 2, k plus 2, k plus 1, x to the k, minus sum k equal 1 to infinity, ck minus 1, x to the k equals 0. And what I can do now is combine these into one ginormous summation, sum k equal 1 to infinity, bracket ck plus 2, k plus 2, k plus 1, minus ck minus 1, x to the k equals 0. And now we use a property of power series. If you have a power series that ends up adding up to the 0 function, that means that all of the coefficients have to be identically 0. So this tells us that ck plus 2 times k plus 2, k plus 1, minus ck minus 1 is 0 for all k bigger than or equal to 1, because that's where it starts. And so we typically solve for the one further down the line, and we get this recursion equation. ck plus 2 equals ck minus 1 over k plus 2 times k plus 1 for k bigger than or equal to 1. And notice we don't have to worry about dividing by 0 here, which in later examples that could become an issue. So we've got the following recurrence relation then. I've got C2 equals 0, and CK plus 2 equals CK minus 1 over K plus 2, K plus 1 for K bigger than or equal to 1. So let's start iterating on this. I plug K equals 1 into it. I get C3 equals C0, C naught over 3 times 2. When k equals 2, I get C4 equals C1 over 4 times 3. When k equals 3, I get C5 equals C2 over, well, 5 times 4. And here's where I know about C2. C2 is actually 0, so that actually gives me 0. Now, when I do k equals 4, I have C6 is equal to C3 over 6 times 5. But I know what C3 is. Well, I know C3 in terms of C naught. So it's C naught over 2 times 3 times 5 times 6. K equals 5, I get C7 is C4 over 7 times 6. But I know C4 in terms of C1. So it'd be C1 over 3 times 4 times 6 times 7. And guess what happens when I get the k equals 6? I get C8 equals C5 over 8 times 7, but I know that C5 is 0, so that zeroes out. So what we start to see emerge here is we start to see that we've got these, some of these coefficients are all multiples of C naught, and then some of them are all multiples of C1, which makes sense. It's a second order equation. We should get two unknown parameters there. Okay, so, whoops, there we go. So our y equals sum n equals 0 to infinity, cn x to the n, which we can write out as c naught plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth plus c5x to the fifth plus c6 x to the sixth. All right, so let's see what we're getting here. C naught we don't know. C1x we don't know. And what did we get for the x squared? So C3, C2 was 0, right? So 0. And then for C3, we got in terms of C naught. And then C4, we got in terms of C1. And then C5, well, that was 0 again. Oops. C6, we got in terms of C naught. Plus C7, we got in terms of C1. C8 was 0. And once again, assuming we're working within the interval of convergence, we have absolute convergence, which means I can rearrange and regroup however I like. So let's get all the stuff that's got C naught in it. And so I'm going to have a C naught, and I'm going to factor that out, and I've got a 1 plus a 1 over 2 times 3 x cubed plus a 1 over 2 times 3 times 5 times 6 x to the sixth plus, and then we'll leave space here because we'll try to figure out the pattern, And then everything else that's non-zero, I can pull a C1 out of. And so what do I get there? I get an x plus 1 over 3 times 4, x to the 4th, plus 1 over 3 times 4 times 6 times 7, x to the 7th, plus, and now let's see, what would the next one be for the C naught? I've got 3, 6, 8 was 0, so it would be an x to the 9th. It would be 1 over what? Well, 2, 3, 5, 6. Oops, give myself some room there. Always running out of room. Let's see. 2, 3, 5, 6. This is x to the 9th. So what would the pattern be? 8, 9, right? It skips 4, skips 7, or it always ends at the power we're at. And what about this one? 4, 7, 10. What would that denominator look like? 3 times 4 times 6 times 7 times 9 times 10, x to the 10th, etc. So we can kind of see the pattern there. These exponents are all multiples of 3. So I've got a 3 there and a 3 there. So that's a 3 times a 1. I got a 6, 6, that's a 3 times a 2. A 9 and a 9, that's a 3 times a 3. All of these guys, if I really wanted to, I could say this is 3 times 0 if I wanted to. Now what about this? There's a 4 and a 4. That's a 3 times 1 plus 1. That's a 3 times 2 plus 1. That's a 3 times 3 plus 1. And if I wanted to, I could think of this as a 3 times 0 plus 1. So we could write this a couple different ways. One of the standard ways we write it is we keep this out, and you'll see why here for a minute, plus the sum k equal 1 to infinity, x to the 3k over 2 times 3, whoops, times 5 times 6, dot, 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 up to, well, let's see, whatever the power is, times whatever the power is before it. So it'd be 3k minus 1 times 3k plus c1 times x plus the sum k equal 1 to infinity. This is x to the 3k plus 1. And so it starts at 3 times 4 times 6 times 7 dot, 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 up to, well, whoops, excuse me, the 3k plus 1 times the one before it. So the one before 3k plus 1 is just 3k. And there it is. And you can show this converges actually everywhere, minus infinity to infinity. Moreover, you can pick off the initial conditions here. Y at 0, well, let's see. If you plug 0 in, these are all powers of x's. Those are going to die. All these have x in it. They're going to die. I'm just left with c naught. What about y prime at 0? Well, y prime at 0, that constant's going to fall away. And the smallest power of x here is x cubed, so it's going to have an x squared. So when you take the derivative, all those x's would zero out. So that would zero out because of the derivative. These would die off because they have x's in it. Here, that x would the derivative of that x is 1. And then here, these are all x to the 4th or bigger. So when you take the derivative, they're all x cubed or bigger. They would die off, and so I get y prime at 0 is c1. This is a very convenient way to express the solution. All right, and so that's one way to do it. There are, and you'll see this in all these systems, the important ones, right? There are actually, I'm going to call it k1 ai of x plus k2 bi of x. There is a certain combination. This is an Airy's function. And this is sometimes called a Berry's function. You can look them up. They're basically scalar constants of these series that are more typical. But what I'd like to do is look at the graphs of these. So this is something I stole from another website that actually took the time to graph these out. I think this is from an SOS math website or something. So these are two linearly independent solutions. So if you look at what the initial conditions would be to create the blue curve, whoops, where did it go? So the blue curve would be a solution where y at 0 is 0, y prime at 0 is 1. So you can see that there. And you notice you've got the oscillation here when x is negative, and then it turns into an exponential when x is positive. Right? So remember the diffie-q here. So when x is negative, we get a y double prime plus y, which is your oscillation. When x is positive, you're just going to get your exponential growth. And if I look at the red one, right, the red one, y at 0 is 1, but y prime at 0 is 0. And so that gives you another linearly independent. And so you have the oscillation and the growth. So that's our first example of a power series solution to a differential equation, and that's Airy's equation.